This is day 20 or day 21. LeetCode every day. Make sure to join the Discord, the Hyperbolic Coding Chamber. Hundreds of thousands of people are joining every day. So, yeah, you might want to get in because honestly, we might take up all the space on Discord servers. We're using up too much memory on their EC2 instance. All right, so there's not going to be a lot of space left on the server, so you might as well join. But it's day 21. I was feeling pretty good about yesterday's session. I think we fried add two numbers. I don't remember. It was a range problem. It was the range problem. And then merge intervals is what it's called. We fried merge intervals. And then we kind of ghetto fried number of islands. I had a brain blast named yesterday's video number of islands equal number of frylands. Feeling good about that one. Is that we almost fried that one first try. Ran out of stack space though. Apparently you're supposed to do a little bit more optimization so that you don't have to waste any more, so you don't exceed the call stack just with how deep you go. So I'll try that one again today to fry it again. And then from there, yeah, we'll try that one again. I'm thinking of the usual, we got the server up. I like what we did yesterday with the whole set time frame for an hour and a half and then do 20 minutes per problem. That seems to work pretty well for me, so I'm going to keep going with that. It allows me to kind of chunk the time up in a better way so we can stop wasting so much time on problems. But other than that, things are going well. The process is proceeding smoothly. The 1 hour and 30 minutes, I think, is peak efficiency time. And yeah, so I'm just going to jump into it. We have one problem, symmetric tree, and then from there we'll do a random weighted, and then from there I'll redo merge intervals, I think, and then from there I'll try to do number of islands again, or yeah, we'll do number of islands, and then from there maybe we'll do another random weighted, maybe we'll touch on another problem. But I think if we do merge intervals and then number of islands again, we'll be able to get those two in the bag, and then we can keep moving forward. And then from there we'll go to LRUCache, just so that the blocking problem. So if a problem is blocking me, I try to do it until I fail, push it down, and then we'll come back to it again. So the number of problems I could be stuck at could be 2 or 3, but that's fine. But I just need to touch more problems. And yeah, other grind things. I received a tip from the Copy Ninja based on the Huberman Lab podcast to try and basically, I think the goal is to bring your upward attention right down to your computer or a wall and stare at the wall for 30 to 60 seconds. And it's going to be a little hard, right, to keep your eyes and to just stare at one spot, right, because usually your attention is following your visual focus. We won't be doing that as part of the practice, but I do think it's a good tip. And I mean, it's a tip from not only Huberman Lab podcast, the buffest scientist on the internet, but also the Copy Ninja. So it's almost doubly valuable. But yeah, I thought that was a good thing to note. I'd be curious if you guys find it useful for your sessions. I know the Copy Ninja finds it useful for his sessions. So yeah, I'm also curious to know what you guys do to get into the headspace to grind. Because I know for myself, I have to kind of find the right, there's a particular headspace I have to be in to do these problems, one that is open to misery and suffering. And sometimes it's a little hard work to get there. So sometimes the inability to do a session is sometimes just an inability to get into the correct state required to do the work the session requires. That's a mouthful. But either way, just saying, maybe life's just about session management. State management. So I'm going to jump into it from here. I don't have any other main bits here. But feeling Gould, I hope you guys are feeling Gould. And don't forget to join the hyperbolic coding. Don't forget to join the hyperbolic coding chamber Discord. Tons of secret insider tips on all the top 3 companies in the U.S. are being traded between inside members all the time. There's some insider trading going on in there. The SEC is trying to get in. It's a whole thing. But I'm gonna jump into it. I'm jumping into it. I'm gonna start both timers. Make sure I'm recording. My screen isn't broken. Okay. So first problem, symmetric tree, goal being linear time, linear space. So given the root of, this one we struggled with. I don't think we knew how to do this one iteratively. Given the root of a binary tree, check whether it is a mirror of itself, symmetric around its center. So you have binary tree, you want to check if it's symmetric around its center. You can check that by seeing if it folds on top of itself. 4 lines up, 3 lines up, and 2 lines up. And we have the tree. Why is this on Java? I never used Java. Oh no, I'm blocking. I couldn't see what I did there. But we have 2, 2, 3, 3, 4, 4. Then we have 1, 1, 2, and 3. And this is not symmetric, even though these two subtrees are technically the same. They're not symmetric, right? And this example 2 kind of is a hint, because we can see that for this to be symmetric, 2.right actually has to be equal to 2.left. So we can see that the subtree connection and checking has to do like subtree.left has to be equal to right subtree.right, and left.right has to be equal to right.left. So I think we can do this with recursion, and our function will take in 2 subtrees, and then from there continue to compare their subtrees to see if they are correct. So here we can just return helper with root.left and root.right. And what we'll do is our recursive function will actually string together a logical series of symmetrical checks. And if they all pan out, right, then we will return true. So we'll have left, which will be a tree node or null. And then we'll have right, which will be a tree node or null. And we will return a Boolean. So now, right, we can imagine, right, we're passing in root.left and root.right. Now we're in here. We have both 2's. We have access to both 2's, right? How do we check symmetricity? The first thing we want to check is if they both exist or don't exist, and we want to make sure there's parity across that dimension. If that is the case, what we want to check is that if left is equal to null and right is equal to null, right, then we can return true, because that would mean that both trees are symmetrical. Neither of them exists. That is technically symmetrical, right? Then we have to check again, right? We have to check one more thing, right? So we want to also check, right, if there is an imbalance there, right? So if they're both missing, that's great, but only if one of them is missing, then that actually means that they're not symmetrical. So if left equals null or right equals null, then we have to return false, right? And since this is an else if, we know that if any of these is true, then we can return false for certain, because we already checked if both of them was true. The only thing we're not checking for is if both of them exist, which is perfect, because what we do down here will make certain that they are symmetrical. So now that we're down here, we both know that they exist. How do we check for parity? This is where the logical string of Boolean expressions comes. The first thing we're going to want to do is make sure that both left and right subtree values are the same. So we'd say left.val equals right.val. Right, so we want to make sure these numbers are the same. There's no point checking their subtrees unless these subnumbers are the same. So if those values make sense, yeah, my Vim bindings are producing just weird outputs, right? And then here you want to do 2 calls of helper, because we want to check the subtrees, but with the correct values. So you basically want to rerun this entire check again, but for the correct values. So we're going to call helper again, but with left dot left and right dot right. And so the goal here is to have now compare 3 for this subtree and 3 for this subtree. Now, if both of them exist, great. If one of them doesn't exist, that's false, right? And then we'd call it again to check left dot left of these, left dot left and right dot right of these subtrees. And so it would keep checking correctly. And then the other one we want to check is if left dot right and right dot left, left dot right and right dot left makes sense. So this recursive function helper, what it really does in the end is string a very, very long set of conditions like C1 and C2 and C3 and C4 and C5, and each C is basically a call of helper. And if all of them are true, then that means this tree is true. But if any one of them is false, then the tree is not symmetrical. So let's run it in our heads for a test run. So we'll do a simple run here, which would be example 1. So we'll call a helper with root.left and root.right. Root.left and root.right will have 2 and 2. Both of them are not null. Both of them do exist, so this would not. Right, if one of them doesn't exist, right, we want to return false. Both of them do exist, so we're good. Then we want to check if 2 equals 2, well it does, and we're going to pop a call of helper onto this, push a pop of helper onto the stack. So now we're going to check 3 and 3. So we have 2. Just to make this make sense, our stack is going to have 2 and 2. These are the current nodes we're checking, right? This call of 2 and 2 made us push on 3 and 3 onto the stack, right? So now that we have 3 and 3 onto the stack, right? Left dot left and right dot right. Are we going to do the same thing? Are they both empty? Are they both non-existent? No. Does one of them does one of them not exist? No, they both exist. So let's check if they're the same value. They are. So now we're going to push another call of helper onto the stack. So we're going to have null and null, right? Well, both are going to be null, right? So we're going to pop that off the stack, right? And since we're going to be back at 3, 3, they want us to do left dot right and right dot left, which is going to push again null and null onto the stack, which is both going to return to true. So we'll pop that off the stack, and then we'll pop 3, 3 off the stack, and we're back at 2, 2, right? Once we're back at 2, 2, we have to check if helper of left, which is 2, dot right, and right dot left, and I'll move this extra space here. And then from here we'll be pushing on 4, 4 onto the stack, right? And then from there we're going to check, right, if both of them don't exist. Well, both of them don't exist. We're going to push. Oh no, I went too fast. We'll be at 4, 4, right? Both of them do exist, so we won't return true, and both of them do exist, so neither of these is going to return at all. So we're going to check if 4 is equal to 4 and helper.left, which is going to be helper.left right here, and helper of right. So we're going to do the same thing we did for 3. We're going to push null onto the recursive call stack. This is both going to return true. Then we're going to do the same for left.right, should be this one, and right.left, which would be this imaginary node somewhere around here. That would also return true. We'd push this off, pop this off the stack, which would return true, and then these 3 Boolean expressions will return true, so we should be good. So that looks good. So this looks good. I'm gonna think that this runtime for this algorithm would be linear time, and in the best case, maybe we do O log of n, because in each case, each call of the recursive function helper, we're working with 2 nodes, which means that we're visiting half the subtree and half the number of operations. So I'm going to say that this would be log n, or maybe I'm completely wrong. I am completely wrong, and the space complexity is bound by the height of the tree. Oh no. I think it's because it's O of n in the worst case. The worst case, the tree is linear and the height is O of n, therefore the space complexity, right? So I guess yes and no. Average case would be log n, but the worst case would be linear time. So follow up, could you solve it both recursively and iteratively? So I think you can solve this. I think you can solve this iteratively. I think you're supposed to use, basically do a depth first search with a queue, or is it a stack? Maybe you could use a stack. You could use a depth first search with a queue, or maybe let's try it with a queue. Let's just say we're using a queue. We're just going to set it to an array, and we're going to use it in a particular way so as to only use it as in a way a queue would be used. That way would be first in, first out. And if that's the case, maybe we start our queue with both root.left and root.right in it. And if that's the case, we could run, right? We'll have, let's say let R1, actually our queue can start empty. We'll just say N1 equals root.left. We'll duplicate this line. N2 could equal root.right. And maybe we'll do while N1 or N2. Actually, no, we'll just always keep going while this queue isn't empty. The queue technically would start empty. So if that's the case, maybe we'll just start it with root.left and root.right. And when we start, we'll just pull these out of the queue. So to get the right one first, we probably want to do it like this. We do queue dot pop. We'll have N1 Q dot pop. So we'd have Q1, we'd have N1 and N2 in reverse, since the order that we have them in is in left first and right first. From here we'd have two nodes that we want to use, or we want to check if they are good. So I think what we can do is take an opposite approach, and before we want to check if things are always true, here we can always check if things are false. If we check if things are false, then we'll know when we want to fail. And since we want to fail, that works well with our iterative version, since we can just return false when things don't pass the rules. So let's just say we check, if we just check symmetry here, and by whatever method we check symmetry, right, for these two nodes, what would we like to do next? We'd like to check the next particular set of nodes for both of these. So maybe we would push maybe we could push left.left and right.left. So we'd be at 2, 2. Maybe we could push left.left and right.left. And then if we did that, maybe if we push that onto the queue, we could then pop the next ones. Actually, I think I'm seeing why we're using the queue. Well, we're not really doing a particular kind of iteration. We just want to visit almost every node in the tree, but simultaneously based off the two nodes we have. So every node that we process has to be part of the respective subtrees. So when we push left.left and right.right, we'd have to make sure that they're symmetrical by passing their nodes. So if we check symmetry, and yeah, and then we could just push. We could just push left, left, and right, right. If we push left, left, and right, right, then we could do right. We push left, left, right. So after we check the symmetry, we push left, left, and right, right, and then we could pull 2 off the front. If we push 2 off the front, if we push left, left, and then right, right, if we push left, left, and then right, right. So if we we'll check the symmetry for these two, and then we push left, left. Okay. And if we we push left, left dot left, and right dot right, and maybe we push left dot right and right dot left, and this just basically will allow us to check each node correctly if we did this for every node. And then from there we would just always make sure to add nodes by going further down. So if we pulled both those off the queue, we'd push left dot left and right dot right. Then we could push left dot right and right dot left. So we'd have null and 3. I'm looking at the failure case here. We could push both of these 2's on, then we'd push 3 and 3 on, and then 4 and 4 on. And then we would go to the next iteration, pop 3 and 3 off, check symmetry, and then push null, null on, and null, null on. Go to the next iteration, process 4, 4, we push null, null on, null, null on, and all of these. Okay, so I think this actually does work. So the queue just helps us to process these in order. So you could do queue dot unshift. No, it'd be q dot shift left dot left, right dot right. We could do left dot right and right dot left. And then here we just have to check symmetry. We'll do it the same way we did before. We're checking for the opposite cases. So if n1 equals null and n2 equals null, and this is a positive case, but we'll just continue here because that simplifies the algorithm, because this part right here is the special part where if n1 is equal to null or n2 is equal to null, right, then we want to return false, right? That's a false for symmetry, right? Another thing we can check for symmetry if the values are not the same. So we can say, or that, we can just do else if n1.val is not equal n2.val. It's another place we can return false, but you can always compress these two. So we push these two onto the front, left dot left and right dot right, left dot right and right dot. So let's just run it real quick. We'll have one. We're starting the queue with root dot left and root dot right. Queue dot length is not 0, so we're going to go in. We're going to pop 2 and 2 off of the queue. We're going to pop right. So if I'm taking things from the end of the queue, this is actually confusing. It's actually easier, I think, if you unshift, add them to the front. If we remove things from the front and we push at the end. So unshift actually adds something to the front. If we remove 2 and 2 from the front of the line, we push those 2 at the end. So we have n2 and 2, both of them exist. Both aren't null, right? So we're not going to continue. Both exist, so both exist, and this one wants to check if either of them don't exist, right? We'll return false. Else if n1, so if their values don't, then we're going to return false. All that is true, so we're going to push 3 and 3 on, and 4 and 4 on. We're going to go back to the top. The queue isn't empty, right? We're going to check in 3 and 3. We're going to check symmetry. So this looks good, I think. Oh, and after we make it outside, we want to return true. And I used with 1 second to spare, I think. Ooh, yes, sir. So this looks good. Queue is an interesting implementation. It's just a vehicle to process nodes together. So that's pretty cool. That is pretty cool. I'm wondering if you could do a similar version of this just to perform like, well, no, actually, this one actually, something that's different about the way we're using this as compared to doing this with a stack that just wouldn't work. I'm trying to figure out what that is. When we do this with a stack, we're always operating on the top one. There's no backtracking to this. The ones that we process are not processed in the exact order. What are we essentially doing? It's almost like we're essentially doing a breadth first search. I don't know, maybe this is how you do a breadth first search, where you'd push on both the children and then take the next one off the stack, off the queue. Is this a breadth first search? If we ignore the double processing part, we go to this node, push these two onto the stack, then handle this node, onto the queue, then we go to 3, add the, yeah, I think this is actually depth first, now that I'm looking at it. This is breadth first search. Instead of recursion, we can usually use iteration with the aid of a queue. Each 2 consecutive nodes in the queue should be equal. The subtrees mirror each other. Initially, the queue contains a root, and the algorithm works similarly to BFS. Each time 2 nodes are extracted and their values compared, then the right and left children of the 2 nodes are inserted in the queue in opposite order. Algorithm is done when either the queue is empty or we detect that the tree is not symmetric without 2 consecutive nodes from the queue that are unequal. Because basically what we have here, this one line here is like pretty crucial because it lets you check if they are different here. For 1, still time is linear time. There's additional space required for a search queue. In the worst case, we have to insert O and I. See, it's a good point with the queue. I should have took that into consideration, but I would count that as a pass. So I'll do a random weighted problem. It looks like it's going to be add 2 numbers. And then I'll set this back to 20 minutes. And we did this problem, I think, a few days ago. But function add 2 numbers. We have 2 linked lists, and we have to return a linked list. We're given 2 non-empty linked lists representing 2 non-negative numbers. So the digits are stored in reverse order, and each of their nodes contains a single digit. So 243 represents a positive number, but it actually represents 342. Each of their nodes contains a single digit. Makes sense? Add the 2 numbers and return the sum as a linked list. You may assume the 2 numbers do not contain any leading 0 except the number 0 itself. So if you add these 2 numbers in reverse, they're starting from the least significant bit. So that makes carrying the overflow simpler. So it's return 7, 0, 8. You can't do a number version of this since the number of nodes is up to 100 and we don't have an integer or a type of integer that can store a number with 100 digits, and the list does not have any leading zeros. That does simplify the algorithm. So it's funny because this is similar to elementary addition, where in that problem you have to add 1 to an array of numbers like this, given 100, 240, 34 in an array, right? And you have to add 1 to it. In that problem, you actually iterate over the numbers in reverse, right, while adding 1 to the number when you run into it. So this would be 235. Basically, 234 plus 1 is 235. In this problem, the numbers are already in reverse order, so I think they're hinting that we should be using this carrying elementary addition approach. So we'll try this elementary addition approach, and the goal here is to add numbers one by one while carrying the overflow. Numbers plus carry overflow. So if we try to figure it out right now, if we do 2 plus 7, right, if we were to iterate over both lists right now, 2 plus 5 equals 7, 4 plus 6 equals 0, right? So once our number equals 10, right, we know that we have to carry a 1, right? So the number of values that we have to carry is actually going to be the base of the number divided by the sum. So it'd be 10 divided by 10, which would be 1, right? But the value we actually place in the number is 0. So what we can do is do sum mod 10. We'll place that in the value here, which would be 0, and we'll continue a carry of sum divided by 10, which would be 1, up here, and then we can add 1 plus 3 plus 4 equals 8. There's one more case we have to worry about, though, and it's when we're adding more numbers that have to be remained in the output. For example, if we add these two numbers as they are, we still get 708 here, but we're supposed to get another 4, right? Because when you add, if you reverse these numbers, right, let's just say you're adding 2000 and 200, as the algorithm works now, we could add numbers on each node, right, by carrying the overflow, but we still have to carry that last remaining number, right? So I think what we have to do is, if we can do some null checking, basically, and what we'll do there is make sure that if one of the nodes doesn't exist, it'll just default to 0, so we can do 2 plus 0 plus 0 and place 2 in the value of the node. So what we're going to do is iterate over both linked lists. Sum is going to equal carry plus L1 plus L2 divided by 10, right? And then we can floor that just to simplify this process in JavaScript. And then carry is actually going to equal, oh no. Carry is going to equal, first we'll calculate, see, this is why pseudocode is a good idea. First we'll calculate the sum, and then carry will be the floor of sum divided by 10, right? So I have the carry, and then the actual value you place in the node will be sum mod 10, and then from here we can go L1 go next, and we'll do L2 go next. So iterate over both linked lists while one of them exists. We'll calculate the sum, the carry, and the value. And then what we can do is actually, they want us to return the new, so we'll just overwrite L1 with value. So we'll just end up, actually we probably shouldn't modify the input. We'll create L3 equals value, and then we still have to add a node for L3. We still have to add a node for L3. So there's a part, if carry is 1, right, I see. So there's probably one more thing we need, right? So if we finish all of these values, right, and we'll probably declare carry out here, right? There's probably one more thing, right? If carry still equals a value, if carry is greater than 0, then L3 equals new list node carry. And so that's another edge case where we still have a carry remaining, but both of our linked lists are finished. So that's kind of like if we add 1 to 9, right? Our loop would run once, but then our value would change to 0, which is fine. We want to add a linked list at another linked list node at the end, which would be 1, turned it into 10. Then we could return L3. So I feel good about this one. I think if we run it for this, I kind of running it in my head as we've been going, but if we add the number, so we declare carry, iterate over both linked lists, so one of them exists, so they both exist here. Calculate the sum would be 7, carry equals 7 divided by 10, which would be 0. Value equals sum mod 10, which would be 7. L3 equals the sum, so that's good. We'd go next. We are missing a line where we need to do L3 equals L3 dot next equals new tree node. If we create a new tree node, then we have to do L3 equals L3 dot next. So we create L3 equals L3's value equals 7. We create a new node. We do L3 equals L3. Yeah, L3 equals L3 dot next. Now at the next node, calculate the sum. It would be L1 plus L2 plus carry. So that would be 4 plus 6 plus 0, which would be 10. Carry would be equal to 10 divided by 10, which would be 1, which makes sense. And our sum would be sum mod 10, which would be 0. We want to place 0 here. We have a carry. We do L3 equals value, which would be 0. L3 next equals new tree node. We create another node under here. We'd go next for both of them. Then L3 dot next. L3 equals L3 dot next. That's good. And then we'd have 1 up here. We'd do 1 plus 3 plus 4 equals 8. Carry would be 0. Because 8 divided by 10 is 0. And value would be sum 8 mod 10, which would be 8. L3 would equal 8. And then L3 dot next. L3 dot next would equal new tree node. Actually, it makes even more sense if we don't do this, but we do, or one of them exists, or carry is greater than 0. Now we run one more time, except we do 0 plus 0 plus 0 plus 1. Carry would be equal to 0. Value would be equal to 1 mod 10, which would be 1. L3 would equal 1. L3.next equals new tree. But we still have an extra null tree node thing. It's always a weird way this works in the end. There you have one more than you want. I guess we could have an if statement, but I don't like how that looks. We have F01 or L2. Then we could create the tree node. That way on the final one for carry, when carry overflows, it would exist already, so we could just set the value. So let's try and put it in because we have 8 minutes left. So we'd have to create output, which would equal new list node. It would not start at any particular value. We'd have carry, which would equal 0, and we have I guess we can just use what they gave us, L1 and L2. So we could iterate while L1 or L2 or carry is greater than 0. it would change L3 to output, and calculate the sum, which would be L1.val, right? But it would nullish coalesce to 0 plus L2.val, which would nullish coalesce to 0 plus carry. And then we could create carry, which would be the math.floor of sum divided by 10. And then value, which would be sum mod 10. And then L3.val would equal value. Here we would say L1 or L2. Then we'll just copy this line of pseudocode, uncomment it. We'll just say, I don't have an L3 actually. Let's just change output to L3. And then L3.next equals new tree node. You'd say L1 equals L1 dot next, duplicate this, okay, NX equals new tree node. So I think this makes sense. Let's try testing it on the first test case. Variable carry used before its declaration. That's interesting because carry is used up here. Oh, I re-declared it down here. That's my bad. Property next. Oh, I used tree node. Oh my god. It's just we just did we just did a binary tree problem. And I used const for L3. Too many syntax errors. Oh my god. Too many syntax errors. Okay, just for the output to fail. Oh, and we also need a, we need to keep a temporary value connected to L3. So we'll just say temp equals L3. That way we can actually return temp. Right, this is what I was thinking of. We'd have an extra output here, an extra 0 that we don't need. And so I try to do if L1 or L2, then create the new list node. But both of these, or maybe it should be done after. Well, no. Well, this one would have to be done. Right, it would have to be done like this. So after we move both of these forward, if there's none left, then don't create the new list node. It seems to pass the first case. I'm going to delete the pseudocode. Let's try submitting it. L2 equals L2.next. Oh, right. We're only running if L1 or L2, so we have to do way more. On the next iteration, we have to do way more nullish coalescing, so they just keep getting pretty much declared to null. And maybe we want the same thing for, I'm thinking honestly that we want the same thing for next. For L3.next, because if L1 or L2, right, then we create a new list node. Otherwise, we'd set the value for carry, and we do L3 equals L3.next, which would still be null, actually, so we're probably safe. We still need to continue creating nodes because it's not that we have to, if carry is greater than 0, we still want to keep creating nodes. So I think we just have to accept it. I think it's if all of these so for all of these, once this final one would come out, we'd have to do L3.next equals new list node, but we end up still outputting an extra node. Maybe this off by 1 nonsense. Why do we keep coming out with this extra node? I mean, I see why. It's because we have L3.next equals new list node. But how do we prevent this from happening? We could do new list node dot off. Always off by 1 errors with the linked lists. It's a little frustrating. Always have an extra body. I know you could just. I think you could literally just do. Maybe you could do L3 equals. You could do L3 equals new list node val, and then you could remove L3. You could do L3 equals. Then you could do L3 equals L3.next. Wait a second. L3 equals L3.next. That way we could just always create the new list node and then go to next rather than setting the value and then going next. So we could just create the value and then just go next. That way we're always safe. So it'd be null. And then when we return temp, temp should fail, but we should have an extra 0 in the front. I meant value. Okay, so I don't think this is lining up correctly. L3 equals new list node. Or maybe we can do temp equals new list node, the head of the list, and then L3 would equal temp dot next, and then we could return temp. There should be a 0 in the front. Of null reading next. Create a new list node. It's kind of frustrating. Create a new list node. Off by 1. We have a temporary node. We want L3 to start at temp.next. Starts at temp.next. Give it off by properties of null. It doesn't make sense though, because if we just created a new list, if we just created a new list node, oh, not L3. Do L3.next equals new list node. Then we connect to it, and then we go next. How are your properties of null reading next? It's always off by 1. I'm so confused. I don't understand why it's off by 1. Can I use custom input? I'm about to use 99 and 9. They should still give me the same problem. So we have basically 99 we have 99 and 9. Okay, so while L1 or L2 we have both values exist and we calculate the sum, it would be 9 plus 9, which is 18, right? The carry would be 18 over 10, which would be 1. The value would be 8. So you'd say L3.next. So L3.next equals new list node. So L3. Oh, I think it's because temp.next. It should probably be like this. I think I just figured it out. L3.next is not supposed to be here. Alright, so now, okay, we're at where we're supposed to be. We're creating a temporary list node. L3 starts at temp as well. And then on each iteration, we create a next node for the list node, and then set that value equal to it. And then we should be able to return temp.next. Jeez. Always an off by 1 problem with these linked lists. I don't get it. So it looks like what I need to start doing is start with a list node, and then my next node in the list will always be newly created. So you can guarantee you can always go to it. So each iteration of this loop guarantees that the node can be the last one. But when I'm creating a node and then going next, it means I have an extra node that you have to take care of, which is annoying. So what I should do is create a temporary node and another node which starts, another variable which starts at that node reference. And then on each iteration, we'll create the next node with the value we want and then move to it. Next, okay, what I was doing before was I would set the current node equal to the value, then create the next node and move to it. So the current node equals the value, which means I always have an extra node. It's not creating it first. I don't know if I can move next to it. The change that's different is we start here, we create the next node, then move to it, create the next node, then move to it, create the next node, then move to it. Create the next node with the value rather than setting the current node to the value. So create the next node, then move to the next one. Yeah, I need to do more linked list problems because this one, that took way too much time. I'm going to read the solution just to... I already understand how the solution works. It's just, I think they did the same thing. They create a dummy head, right? Cur equals dummy head. So maybe this helps. If I create a dummy head, cur equals dummy head, that way you always create the new list node with the value, then go next. Okay, Gould enough. We'll pass that. What did I say I was gonna try? Put another 20 minutes on. I said I was gonna do add two numbers. We did that. Did symmetric tree. This is the problem list. So restarting here with merge islands. Feel good about this one. I think we can solve. I just deleted the code, but basically, I mean, starting over from scratch basically. So we have function, num islands, we have a grid, we have a multi-dimensional array, we're supposed to return a number. Given an m by n 2D binary grid, which represents a map of ones and zeros, water, return a number of islands. An island is surrounded by water and is formed by connecting adjacent lands horizontally or vertically. We may assume all four edges of the grid are all surrounded by water. All the four edges of the grid are surrounded by water. An island is surrounded by water and is formed by connecting adjacent lands horizontally or vertically. So we can see that all these ones here connect to this group of ones here vertically through 1, 1. And that is perfect because that means there's one island. Here we have one group of islands in this four corner. And then we have another island here, right, because it's not connected to any of these other islands vertically or horizontally. We have one more island, which would be, output would be 3. So I think what we can have is a pretty much, if we visualize this two-dimensional grid as a graph, we can do a depth first search basically. I don't even call it depth first search. I think we can use recursion to check the surrounding areas, right? And if we check an area, right, and it has to be, turns out to be a 1, so if we find a 1, right, it means there's a start of at least one island confirmed, right? So we'll have islands. If we find at least one 1, we know that we have at least one island. From there, we basically want to clear out all possible ones connected to this island. To do that, we're going to do a recursive function where we check up, down, left, right for every node. So we have to make sure that we don't go outside of the bounds. I forgot to start the timer. Outside of the bounds, because that counts as water. So we go to 1, turn it to a 0, and we have to turn all the islands we visit to zeros, right? So that we know what's an island, what isn't a possible island. So we turn this first one we found into a 0, right? Then we'd go right. But we try to go up, but we can't go up, so we'd go right. Then we turn this one to 0, we try to go up, we can't, we go right, it's already 0, we go down. So we go to this one, turn it to a 0, we try to go up, well it's already a 0, then we try to go right, it's already a 0, we try to go down, it's already a 0. We go left, we turn this 1 into a 0, we try to go up, it's a 0, right, it's a 0, down, it's a 0, left is out of bounds, we pop back to this one, go up, it's already a 0, pop back to this one. We go left, it's already a 0. We go up, it's out of bounds. We popped out to this one. Go down, it's a 0. Left is out of bounds. Up is out of bounds. So we know that we're going to need a basically a recursive function, and we're going to have let islands equals 0. We're just going to have to iterate over the entirety of the grid. So we'll just say row equals 0, right? Row is less than grid dot length. Row plus plus, then we do call is equal to 0, call is less than grid sub row dot length, right, and do call plus plus, right, and we know that once we find at least a 1 from where we currently are, right, that's going to trigger a depth first search for this recursive function to find and clean the local islands, right? So if row sub call equals 1, then we want to kick that entire process off, and we're just going to call it clean. First, we want to increment our islands because we know that we found at least one island. We just want to clean the local islands on the local island regions on the map to simplify the algorithm. This also speeds it up. So we call clean islands with grid, row, and call. So clean islands is going to take a grid and multi-dimensional array of strings, row, which is going to be a number, and call, which is also going to be a number. It's not going to return anything. And so first things first, we have to check if the one we're processing, if the row we're processing is a valid row, right? So if our row is less than 0, right, or our row is greater than row.length, probably greater than or equal to, right, row is greater than or equal to row.length, right, or grid sub, to get the column length, you have to grid sub row dot length, right? Same thing if it's less than 0, or if grid sub row dot length is greater than or equal to call, right? Then we want to just return. We don't want to do anything. And in fact, we could just call this validate cell, and we could just pass in row. We could just pass in grid string and do row number call number, and it could return a boolean. And we just need to run this code basically multiple times, right? So we want to check if validate the current cell we're in, right, with row and I'm gonna push this forward a little bit. So basically, if any of these returns true, this row is not valid, right? So we'll just call cell is valid or cell invalid, right? If any of these are true, the cell is invalid, right? So we'll say if cell invalid, right, then just stop, right? Just stop it. Get some, so, right, so if cell's invalid, right, then we just want to stop it and get some help. And then we want to check the surrounding areas only if they're not a waste of time, right? Before that, we want to mark the area we're visiting. So now we know that the area we're visiting is valid, right? So we're just going to mark the row and column, right, equal to 0, right? Because we know we ignore zeros. Because we don't want to trigger another search if we run into a 0. And then, right, we'll have if the next cells, right, so we have to do this check where we do up, right, left, down. So if the next potential cell is not invalid, so we'll pass in grid, we'll do row. We want to check above us first, right, so we'll do row, right, call plus 1. Call plus 1. Then we want to do clean islands, right, grid, row, call plus 1. Duplicate this 3 times, and we also want to check up, right? We want to check to the right of us, which would be row plus 1. With column staying the same, we want to check below us, which would be exactly where we are, where the row-wise, we'll call -1. We want to check to the left of us, would be row -1, but exactly where we are in the columns. We'll change these parts to mimic what we just wrote. We'd have +1, -1. And so this looks good to me. And yeah, we just want to make sure that we clean out all the zeros, and then we'll return islands. I don't want to blind run this just because it's a bad habit. We'll run it really quick for example 1. So we're going to iterate over the rows, right? It's going to be the grid.length, right? And the columns for this row, so we get 0. the column would be, the length would be 5. So if grid sub row sub col, which would be 0, 0, 0th row, first column would be 1. It is islands plus equal 1. We'd clean the local islands, right? Is the cell invalid? We have row is not less than 0. Is row greater than, is 0 greater than equal to 4? No. Is grid sub row dot length, which is 5, less than 0? Nope. Is 5 greater than or equal to column? No. I mean, yeah, is 5. Oh, no. Yeah, it's 5. Yeah, because the length of it is 5. Is grid sub row dot length, it should be 5. Is 5 less than 0? No. Is grid sub row, which is 5 dot length, greater than or equal to col? Which is 0. Yes, so the cell is invalid. That's not true. So something's off here. We want to make sure that col is not less than 0, and that this is why it's good not to blindly run things. Col is not, and if col is greater than or equal to grid.row.length, then it's invalid, right? And it's 0, so it's not, right? So the cell is not invalid. We'd return false. We'd mark it as 0 and check if the next ones are invalid. We check row and col plus 1. That would be valid, so we call that. Clean islands, grid row, call, grid row. So this looks good to me. Let's try giving it a run. Length does not exist on number. So line 2, length does not exist on number. So if we do grid sub row, we should get an array of numbers. But it's saying that length does not exist on type number. So grid sub the first should give us this array of numbers dot length. It's not, cannot find name cell. So something's just wrong here. Line 6. Oh, I have cell. Okay. So I change this to call. Property length does not exist. Oh, I did row dot length. Ah, I caught the first one, but skipped. It would be grid. Ah, man. Minor grid dot length, which would be the number of potential rows. The maximum call stack is exceeded. So the same issue I had before. Clean islands. So there needs to be, I guess I'm not, if the cell is invalid, we also don't want to run this if, right, so after this point we know that row and col are validated, right? Or grid sub row sub column, right, equals, if it equals a 0, right, then the cell is invalid and we don't want to waste any time on it. Basically, we want to skip anything that's not a 1. So let's try this version. Let's see if this version. So that looks good. We're skipping anything that's a 0 now. I wonder if we get call stack size exceeded. All right, let me stop. But okay, number of Frylands. Okay. So I see we also want to skip anything where there's a 0. And we want to do that for every iteration. I want to do some testing. I want to see if I delete this whole block and see if I run out of stack space, if I run out of the call stack. And if what I really needed to check was really giving us way more calls, was that I have to make sure that you have to validate the cell. And if the cell is a waste of time, then don't trigger depth first search. So that would be row call equal. I think before what I was doing, I was checking if the cell was out of bounds. I wasn't checking if it also equaled 0. So I would call. You'd go through these calls again, but it would I would keep going infinitely because I'm not knocking out zeros. So this looks good. Feel good about the solution. It took like 14 minutes. Treat the 2D grid map as a undirected graph. Okay. And there is an edge between two horizontally or vertically adjacent nodes of value 1. Undirected graph. So you can go in any direction. Linearly scan the 2D grid map. If a node contains a 1, then it is a root node that triggers a depth first search. Makes sense. During depth first search, every visited node should be set to 0 to mark as a visited node. Makes sense. Count the number of root nodes that trigger DFS. This number would be the number of islands since each DFS starting at some root identifies an island. And we're removing, based on the trigger of a depth first search, any potential retriggers. So 1 triggers DFS, then we'd all right. So in this one, how does they validate it? Oh, and it equals a 1. That's interesting. I see what they're doing here. That's interesting. They're making sure that the next grid that they're potentially travel to should trigger depth first search by equaling 1. That is interesting. I think that is much simpler than mine, actually. Because what I'm really doing by making sure that the cell equals 0 is the same thing they're doing by making sure the cell equals 1. I want to skip them if they equal 0. They only want to do it if it equals 1. So it's the same thing, basically. But theirs is a bit cleaner. Interesting. Interesting. So it'd be m by n because we're visiting every element in the node in the grid, but the space would also be m by n because, you know, potentially the worst case is that every element in the grid is an island, and so you would actually trigger m by n calls of clean islands. You can do this with breadth first search as well. That is very interesting. Interesting. So we have some time left. Number of islands is fried. Did we do merge interval? We did merge intervals the other day, I think. I think merge intervals is already in the... I actually don't know if it's already in the code, in the card-based thing, but it should be. There's 20 or so minutes left, so I kind of feel like we should do... I'll just close this since there's just 20 minutes left. I kind of feel like we should do LRUCache. So we'll try this. Design a data structure that follows the constraints of a least recently used cache. Implement the LRUCache class. LRUCache int capacity initializes the LRUCache with a positive size capacity. Int get int key, return the value of the key if the key exists. Return the value of the key if the key exists, otherwise return -1. Okay, so we have a cache, right? It's least recently used, so the capacity is the number of elements we can keep in the cache, I guess, and return the value of the key if the key exists, otherwise return -1. Update the value of the key. If the key exists, Otherwise, add the key value pair to the cache if the number of keys exceeds the capacity from this operation. Evict the least recently used key. Otherwise, add the, oh, I see. Otherwise, we add to the key. So if we're going to add to the cache, and this key would put us over capacity, then we want to trigger an eviction. These functions get and post must each run in constant average time complexity. Well, you get input for free using a dictionary or a map. So it really needs to be, the fact that put needs to run in constant time is interesting because we need to know basically if we should evict this node. We need to know if we should evict this node. If you only use a map, you never really know if you should evict. If you only use a map, then you can't really get the least recently used one in constant time. If you used an ordered map, maybe ordered map sticks out to me. Hash is 1, 1, put to 2, get 1. So we'd get the value for the key 1, which would be 1, right? We'd put the value 3 for the key 3, but since 3 didn't exist in the map, right? The last recently used key was 2, right? So cache is now going to be cache is now going to be 1133. And we get 2, right? Returns -1 not found because it was evicted because we went over capacity. If we put 4, 4, now if we put 4, 4, the LRUQ is 1, evicts key 1, cache is 4 equals LRUQ is 1, which evicts key 1. Not found, so we put 4, 4. The LRU key was 1. So since 3, 3 is still in there, the last recently used key was 1. So we basically need a way that if we run get, right, the LRU key was 2. So if we run get or put, then we want to be able to know, right, the least recently used key almost instantly. So how do we do that? I think we could do this with a linked list and a map, and the map, right, would store instant references to where the map would store an instant reference to where the node is for the key, right? So we could have a linked list, right? And this linked list, whenever something needs to get evicted, so let's write this down. We'll do an LL map combo, right? And whenever something, so let's just map this out in, we already know that we're going to need capacity, right? We're just going to say capacity equals 0, right? And the constructor will say this on capacity equals capacity. So when we get, we want to move, so if this key exists in the map, right, move it to front of LL, right? And so the map will allow us to basically instantly get where we need to be in the linked list. And since we can do that, we can move it to the front instantly. And then we could return -1. If it doesn't exist, then we will return value of node. Right now, when we're putting a value into the LRUCache, what we want to do is check if cap +1. So we'll just say, you know, if key in map, right, we can check if capacity, so they'll say If the number of keys exceeds the capacity from this operation, evict the least recently used key. So I think capacity would actually stay the same. We just remove the last one. Right, so it sounds like once we reach capacity, it is what it is. So if the key, else if, right, else, it looks like we do cap plus equals 1. So if the key, so if let's do with the, if it's not in the map first, right? So if it's not in the map, then what do we want to do? We want to add it to front of LL, which means that it's the most recently used key since it was just added, right? Actually, it's interesting. I think it would actually be the opposite. We actually don't want to do if keys in the map. If key is in the map, then update node with the value move to front of LL, right? So we update the node, the value, move it to the front, right? If it's not in it, right, then we want to check, right, if it's not a linked list, right, then there's two cases, right? There's two cases. The one is right is that if cap if keys.len less than cap, right, then we want to add node to the map, right, move to front of LL. So I'm starting to notice there's a little code duplication here. Maybe move to the front of LL is just something that's going to almost always happen. And I think do we have to worry about put validating key? And then there's another thing. Node to the map, move node to front of LL, and then there's another case where cap is greater if current, or I guess we could have, let me create a binding real quick, running out of time. Let's create a max capacity equals capacity, capacity equals 0, and then we can say if capacity is greater than max capacity, if capacity is greater than max capacity, then we want to evict the least recently used key. What does that look like? We would grab node at the end of the linked list, right? Delete it. Grab node at the end of the linked list. We would delete it, and then delete it from LL. Then we would remove it from the map. And then actually it looks like it seems like we always want this to happen actually. So it's not that it's less than capacity, it seems that we want to add the node to the map, move to the front of the LL, and if capacity is greater than max capacity, then we'll grab the node at the end of the LL, delete it from the LL, and remove it from the map. So in 10 minutes, let's try and see if we can implement this real quick. I think this makes sense. If we put 1, 1, then we have 1 in the map, 1 in the linked list. It has to be a doubly linked list, so it's simpler to add and remove. We have update, so we put 1 1 in the map. So if the key is in the map, it's not. We'd add the node to the map, move to node front, move it to the front of the LL, and then we'd have capacity. Oh, so another thing we have to do is do capacity. Capacity plus equal 1, and then capacity is greater than max capacity. Then we could do capacity minus equal 1 if it exists. I mean, if that is true. And then, so we would add it to the front, add it to the map, add it to the front of the linked list. Capacity plus equals 1. Then we do the same thing, add it to the map, move it to the front of the linked list. Then we get 1, we return 1, we put 3 3. So we put 3 3. The key is not on the map, so we'd add the node to the map, move the node to the front of the linked list. Capacity plus equal 1. Capacity would now be greater than 2. Grab the node at the end of the linked list, which would be 1. Or actually, so we'd put 1, we'd put 2. So 1 was at the front, then 2 is at the front. So 1 is at the front and 2 is at the front. We always delete the node at the end. We put 1 at the front, then put 2 at the front. We put 3 here. They want us to remove 2. I see. So we actually want to always remove the node at the front of, okay. Add the node, so if this key exists in the map, move it to end of LL. End of LL. So we'd have put 1 in, it'd be at the end of the linked list. Then we put 2 in, 2 would be at the end of the linked list. We'd get 1, we'd be fine. Put 3 3. We want to evict key 2, so you want to grab the node at the end of the linked list, which would be 2, leave it from the LL, remove it from the map, and capacity minus equals 1. Then we'd get 2, but it wouldn't exist, so we'd return -1. Then we put 4 4. Put 4 4. It wouldn't be in the map. We'd add it to the map, move it to the end. Capacity plus equals 1. So we'd be at 2 again. Then we'd get 1. Oh, well, we'd have, wait. Right, so we'd evict 2. We'd put 3 back at the end of the linked list. Get 2, it wouldn't exist. We'd put 4. We'd put 4 at the end. No, we'd, basically, okay, we have 1 and 2. New nodes get added to the end of the linked list. We have 1 and 2, so 1 and 2 is at the end. We put 3. We add it to the map, move 3 to the end. Capacity is great. We grab the node at the end. Node at the end. I think I'm getting confused. There's some places where I have front, some places where I have. So whenever we add something, we add it to the end of the linked list. We'd have 1, and then 2 would be at the end. When we get LRUCache for 2, we get check the cache. We put 3, right? We have 1, 2, and 3 would be at the end. What do we want to remove? We want to remove. Right, so we put 1 at the end. Put 2 at the end. When we do a get, right, we'd put 1 at the end again. So now 2 would be at the front of the linked list. And so we want to grab the node at the front of the linked list, delete it from the linked list, which would be 2. now we'd have 1 and 3 we'd get to, which wouldn't exist. We'd put 4, and the LRU could be 1, so we'd evict 1, so the least recently used will be kept at the front. So I think we can implement this. We have 5 minutes. I think you automatically get a list node implementation. Class dList node equals val, which is a number, and we'd have prev, which would be a dList node or null, and next, which would be a dList node or null, and we would have val, which equals 0, and next, which would be equal to null, pre, which would be equal to null. We have this dot val equals val, this dot next is next, this dot prev equals prev, so we'd have this list node. I'm just gonna run it just to make sure that basically that my class declaration makes sense. Okay, so that's good. It doesn't work because I'm just about to, so we'd say DLL equals new dList node, and then we'd have map equals new map of number to dList node. So let's just implement if we get a key, right? If the key exists, so if map dot has key, right, then we want to move it the current node, so we'd say const node equals map dot get key. So now we have a node with previous and forward, right? And so we want to move it to the end of the linked list. So we'd also need a head and a tail, otherwise you never know when you're finished. In the constructor, we'll say this dot head dot next equals tail, and we'll say this dot tail dot pre equals head, so we'll have head and tail. We want to move it to the end of the linked list, so we'll create a temporary variable which is equal to head, and you want to go while temp dot next does not equal null. Temp dot next equals null. Oh no, we actually already have access to the node. So we have access to the node. We want to move it to the end of the linked list. So we would say const temp equals tail dot previous. So we keep a reference to the previous node where tail was at. So tail dot previous equals node dot next equals tail, and then node dot previous equals there's like so many pointers you need to change. You change the next pointer that we're pointing at. So right, we actually have it. It's tail.prev at a time. We have tail.prev, which would be the node right before us. We want to insert the node where we are, so tail.prev equals node, right? Now points to this. Node.next now points to tail, and we want to say temp.next now points to node. So now it's at the end of the linked list. right? And we also want to say map.set key equal to this node. If this key exists in the map, we just want to move it right to the end of the linked list. So this is actually would be in the else. We'll say return map.getKey .val, which should return the value of the node. This key exists in the map. We need functions for this to simplify it. Node and temp, so we'll push both. So moving it to the end of the linked list and returning the node. Then we return get the key, which will give us a node, and then we return the value. If the key doesn't exist, you still want to move it to the end of the linked list, basically. Basically, you want to move it to the end of the linked list anyway. So it seems like we can actually pull this stuff out here, and it's if the map has the key, we always want to move it to the end of the linked list. Or oh yeah, if the map has the key, you want to move it to the end of, oh yeah, I got confused. You don't have to do anything with the map. You gotta follow the pseudocode. Move it to the end of the linked list. Return map.key .val. Now, if the key is in the map, if map.has key, then we want to move update node with the value. We'll say const node equals map.get key node.val equals value, and then we'll just copy this code to move it to the end of the linked list. I don't think this is going to work first try, and if it doesn't exist, then you want to add the node to the map, so we'd say node equals new dlist node value. We want to move it to the end of the linked list. Say capacity plus equals 1. And if capacity is greater than this dot max capacity, then we'll do this dot capacity minus equal 1. We want to grab the node from the front of the linked list. This would be front equals head dot next. We want to delete front from the head of the linked list. Grab the node at the front of the linked list, delete it from the linked list. Deleted from the linked list. If we're at the node that we need to delete, it would be head equals head head dot next equals So we can just say head.next equals head.next. So we have a node, when you want to delete it, you could say head.next equals head.next.next. Then head.next.next dot prev equals head. If head.next. Then we'll say head.next next dot prev equals head. And then we'd say map.delete t. Yeah, this is just a Hail Mary, so we'll see. Line 16. Oh my god, I didn't use any thises. We don't need them here. $21. It's not gonna work, but I don't even know why I'm still I'm in two different scopes here, so I'm not understanding why it's complaining. line 87 is not even part of my code. Cannot redeclare blocks code variable node. Yeah, okay, I figured this was wrong. -1, -1, -1, -1. So it is what it is. I'm gonna try this tomorrow, so